Morning, Gerhard Fettweis. He is the Vodafone Chair of Communications at the Technical University of Dresden. He's on sabbatical right now at Berkeley. I think one thing that makes Gerhard unusual is that he has a background in circuit design and for many years worked on a system on chip type research and also has expertise in communications and networking theory. So his expertise is very, very broad, and as a result, his lab has been extremely innovative and churned out over many years a lot of interesting intellectual property, 10 startups, and so he's somebody who really spans both theory and practice, I think, like almost no one else in our industry. And so it's a great pleasure to welcome Gerhard here to speak. Gerhard.
Thanks, Jeff, for this wonderful introduction. And let's see if we can get started. So, what I want to talk about, obviously, is 5G, and I will not be talking this time about 5G at 100 to 300 gigs carrier frequency, because I would not stop at 60 gigs with 5G. I would clearly move it way beyond that. But I will be talking about just one aspect of it, which is, I think, an innovation that is going to happen and that's going to change our planet. So I'll talk about the Tactile Internet and its technology, and let's have a look at what has been evolving. So if we look at here the election of Pope Benedict in 2005, this is Via della Conciliazione, everybody waiting for the election result, and this is Via della Conciliazione a couple years later when Pope Franciscus was elected. So obviously we see there are two people on the left picture using a phone, and on the right picture, nobody's using a phone. Everybody's just using a camera. If we were to connect all these phones into the system, obviously it is clear that we need higher and higher data rates. Yes, it is totally clear. So this wireless roadmap that I started sketching in 2003, at the time when I was chief scientist of Philips Semi, we basically, people almost killed me for that in 2003 within the company. But still, we see the data rates are increasing 10x every 5 years, doubling every 18 months, Moore's law. And it's not a question, do we need this? We do need this because with the picture that I showed before, we need terabits per second in small networks, small areas, just to download, upload, whatever the capacity that we need to run these kind of applications that don't work these days. So now the question is, however, is this the only thing driving our industry? Yes, this wireless roadmap obviously does drive the industry, but is that the only thing? If we look at it in a sort of a three-dimensional space, we see that it drives the axis going upward, massive content, yes, going to speeds of 10 gigabits and beyond. We need that, and we need a terabit Wi-Fi pretty soon as well. But in addition to that, we see now with, for example, Cat-M, narrowband, and others things happening right now that we will have massive sensing applications also available in a 5G system. We'll see it starting, as I say, with LTE Cat-M, starting probably in 2017, sort of growing the market from there. But then we will see it also being a massive part of 5G. So connecting every flower pot, every sensor on the planet into a 5G kind of network. Because anybody that has built Zigbee-based systems knows how cumbersome that is and how flawed that is. So finally, if we have an open standard that you can connect to with any kind of device, that will change the planet massively. And then the third axis will be massive control. But the good news is we don't need all three simultaneously. Yes, we don't have to run a 10 gigabit per second modem of a AAA battery and it has a millisecond round-trip latency. So the good news is the applications do meander around, and you have the flower pot does not need a 10 gigs interface and doesn't need a millisecond. The video application of the future do need these massive data rates, but might not need the latency, et cetera, et cetera. So we see there's a trade-off here, which for us engineers makes this feasible. So let's have a look at the lower axis, getting the latency down, because I believe this is yet another step that is going to happen And it is happening right now, but it is happening sort of in a subtle way without people really noticing it. And the idea behind it is the following. When I started thinking about this about 6 years ago, it was, well, you take your phone out of your pocket and say, so it's higher and higher data rate, what can you do? Higher and higher data rate. Well, what is missing here in terms of this interface? It is totally unclear. And it turns out that if we look at how telephony is built, we hold it to our ear, we can talk, and it's built on this 100 millisecond latency between my phone and your ear, and then we can do real-time communication. And that is very good, because this way we can interact. I can interrupt you while you're talking, and you interrupt me while I'm talking, and this seems to be natural. If we look at the speed of sound, which this means we can actually interact standing 30 meters, 100 feet apart. Yes, that is exactly the 100 millisecond is 100 feet distance of sound. And that makes totally sense for us from a biological point of view as humans, that we want to be able to interact. However, there's another thing. Our eyes are right here next to our brain, and why are they so close, and what is it? Because if we touch and feel an object and move it, our eyes don't want to wait for 100 milliseconds to see this object move. It turns out we need it much faster. We need it in the millisecond range. And if we take an LTE system of 50 millisecond range, round-trip range of reaction interactivity, that means we really have to go down by at least 1 order of magnitude. Now the question is, where does this millisecond sort of happen today, and where do we see a subtle way of this millisecond interactivity being so important? It is in gaming. If you look at a gaming party, they do not do internet gaming over the Atlantic via the Pacific or whatever. Why is that? Because the speed of light is too slow. Yeah, the speed of light is extremely slow. That's why we wireless engineers have so much to do. That's why we have inter-signal interference and all these other things. So light travels only 200 miles in a millisecond, or 300 kilometers in a millisecond, which is nothing. And that's why in these kind of gaming interfaces, gaming parties, you need a 10 millisecond reaction time, otherwise the gamers are totally unhappy. And that's why they start having these kind of gaming parties, not only for the social effect of it, but really to get the latency down to these kind of systems. And let's have a look at us humans catching a ball. You see here goggles and a camera mounted in front of the goggles, and we can sort of set up the latency. Now we set up the latency to 150 milliseconds, and you see it's not really fun trying to catch the ball, because we actually, what is it? And now we put it down to the minimum latency in this setup, that's 5 milliseconds, and you see the ball is caught with about 5 centimeter displacement. If you throw a ball like that, it travels at around 10 meters per second, which means a centimeter distance is 1 millisecond. So per millisecond it travels a centimeter. So if your latency is more than a couple milliseconds, you're not going to be able to interact in real time. Yes. I mean, if you, as I always like saying, if you're a famous Buick driver, you're used to pulling on the steering wheel and things happen maybe a couple seconds later and you get used to that. But if you then get into a Porsche, it's the difference. So the whole thing about this is if you then start operating like these kind of robots, remote control robots, and you've tried to do that, you see it's scary because you move these knobs and the thing jumps around like crazy, and you have to start learning to use this. We need this low latency, but we also don't know how to move this. Now, if we were able to get a wireless interface down to a millisecond reaction time, then we could move to humanoid robots and have humanoid robots walk into that situation. They can clean up the situation as we need. So basically, you just see the situation with your goggles, looking through the eyes of the humanoid robot. The robot copies your movements, and you do whatever you want to. You clean up the suitcase left over in the airport. You do a hazardous cleanup in Fukushima or whatever all. Basically, with this kind of interactivity. And that obviously is something everybody of us can do. And with these humanoid robots going to a price tag of $1,000 soon, we'll be able to actually see this, making our life very different and very easy. Then obviously the next situation is trying to see if we can have haptic feedback as well. So we need to be able to understand what is the human touch and feel reaction time that we need. And it turns out, if you talk to physiologists and psychologists, not only our visual interaction, but our touch also needs this millisecond latency. Then we can take this soft thing, move it around, it feels as if it was a piece of metal, even though it's soft, and it doesn't fall down. So with this kind of setup, we can actually extend our personal reach completely into a different way. So today we can extend our personal reach in terms of talking and browsing the web. Tomorrow we will be able to extend our reach physically, and that is a big step forward. With this kind of a view, let's have a look at other applications where this millisecond plays a major role today already, and where physics shows us that we basically are this. This is in electronic stability control of cars. If we have two wheels of the car and we want to make sure we go around the corner and the car should stop skidding, we have to synchronize the braking of the wheels with an ESC system, and it turns out that this is a 1 to 2 millisecond delay problem. Why is that? Very simple, physics. Right? The resonance frequency depends upon the wavelength. The distance between these wheels is 3 meters. A 3 meter means 100 hertz, 50 hertz resonance frequency, lambda half. So 6 meter would be the wavelength. That means 50 hertz. That means a 2 millisecond latency because we have to sample 10 times per period to be able to control any resonance that is happening due to a nonlinear effect. And here, due to the gravel on the road and whatever all, we don't have a simple linear second order system, but we have a complex system, and so that's why the ESC is exactly going to the rule of thumb of robotics. Now, if we then want to go and say, we want to go to autonomous cars, and we see this happening, the big news again now with Tesla showing us autonomous driving. What happens if we go to autonomous cars? It turns out if you talk to Bosch, they say, and they provide a lot of the electronics, they taught us quite some time ago already that it's okay, it works, but it doesn't solve our problem. Why? What's the problem? Well, if we want to be able to platoon cars, what do we have? If you're sitting in the second car in a traffic jam or in a row of cars, what do? You accelerate, you brake, you accelerate, you brake. You continuously sort of do that and keep a certain distance. Now, if you want to compact this, what happens? You get this acceleration, deceleration, second order system of the first car, the second car, and the third car starting to be coupled. The first guy starts pushing the brakes exactly while you in the second car are accelerating. You overreact, slam the brakes, and what you have, you don't necessarily have an accident, you have just a traffic jam. That's theoretical physics at its work, explaining traffic jams. And now if we have 3 second-order systems, we just barely can manage it. Anything beyond 3, control theory, theoretical physics tells us it becomes a nonlinear, uncontrollable system that becomes sort of chaotic. So what we have to do is we have to build an ESC system where all these cars are platooned together at the millisecond range, 2 millisecond range. Otherwise, the system doesn't work, because otherwise the first car starts skidding and the second and third get all messed up. Now, if we built this as a car-to-car kind of connectivity system, that's one possibility, but then obviously the Peugeot up front is controlling the Mercedes in the back, and they don't like that. So that's one reason, and the other problem, obviously, it's an n-square connectivity problem. So it's much better and easier just to build an infrastructure and be able to have these cars hooked up and disconnected via an infrastructure that guarantees exactly the quality of service that we need. And the number of connections, of course, in a star network are way smaller. Now, if you think that this second-order problem is not there. Here, just a short video. We had a couple 9th grade students come to our labs and set up with Lego Mindstorm this little experiment. You see here these robots driving along the track. They keep a certain distance, making them decoupled, and everything is fine, and the music shows you that they're in a good mood. Now, what happens if we want to show that this coupling happens? So what we see here, we put in a disruptive element, which is the cardboard box. The first car stops, very nice. The second car stops, the third car seems to be okay, the fourth car starts wiggling and jiggling, and now the first and second and third and fourth are also soon going to start jiggling and moving around. And this is not exactly what you want to be in if you're sort of in a Tesla, driving in a platoon, and suddenly you start jerking back and forward. Which tells you autonomous driving is fantastic in fluffy traffic. But in dense urban traffic, where we exactly want this to be, in fluffy traffic, we like driving ourselves. In dense urban traffic, we want the car to take over. And then it doesn't work. So we need this millisecond control infrastructure to be able to do that. And then obviously, we can also get rid of traffic lights and just have everything zoom around. We have a personal bubble. We cross the street. And no car hits us, we can guarantee that, and we even could implant this, obviously, cellular device in a frog, and it's happily crossing the street. If you think this is pure fiction, here you see that it is not pure fiction. Here you see a regular traffic intersection, and now we turn on the tactile internet, and now we see the efficiency of this whole system. It's absolutely fantastic, fabulous. Just think of driving along there and you're safe and everything's okay. If you don't believe that this can happen, then go to Leuven in Belgium and just as a pedestrian try to cross the streets with all the bicyclists around. You basically have this kind of Indian Bangalore or Delhi kind of situation. And if you see, basically, now I'm crossing the street with my backpack. It was a tight squeeze here right there, yes, but I survived, as you can see. Anyhow, this is not real. This is a fake video, obviously, done by Fernando Lifshitz from Bullshit Films. But just to give you an idea of what this is. If we then move into the next application, let's have a look at what robotics can do these days. So this is Timo Boll, the world's champion in ping pong, playing against the newest KUKA robot, the Agilus. And so here you see basically the reaction time of robotics as it is possible today. And if you want to, it's a whole match. In the end, the robot wins, obviously. And just to show you the capability of robotics is coming to this space. And if we look at this robotics, what does it is? What does it have? The robot arms, again, are around a 1.50 meter size. Again, we have to control it because of resonance frequency. So in robotics, everything is about a millisecond control. If we then look into a factory of today, we see these robots sitting there with a millisecond control wired up. And people don't want that anymore. For two reasons. One reason is those cables break. And the second reason, obviously, is we can manufacture one thing many times, but not a large variety. So we want to go back to an assembly station, away from the assembly line, to be able to manufacture individualized products and goods in a way that we want to have it. We want robots to whiz on the ceiling and on the floor, and just assemble on time, in time as needed. So these whizzing robots, again, have to be controlled in the millisecond range. Otherwise, we have this nonlinear buildup of systems that doesn't function. If we then take this, we can have individualized products of a different stage. Yes, you're standing in front of your mirror, you're seeing yourself in the mirror, hopefully with a millisecond latency. And then you move around and see then whatever you choose. You have a designer standing next to you, an artist that finally has a job. And that's why I say it's a job machine. And then you basically go ahead and decide this is what I want, and then it goes to your individualized manufacturing machine, and then we have what we want. Now, just to show you that a virtual mirror doesn't need a millisecond latency, here is sort of what is available on the web, yes, showing off the fantastic idea of this virtual mirror, but obviously the millisecond latency is not really there. So you get some interesting effects. Not everybody's a sort of personal choice if you're standing in front of that mirror, but you see we need this millisecond continuously all over the place. Now, I think one of the other areas that I find very exciting is precision farming. Yes, farming is probably the most widest implementation of robotics on the planet. So if you look at this, what do these guys do? They harvest, and they want to make sure that they hit the same track every year again, because the densification of the ground, compacting the ground, has to be hit by 1 inch preciseness. Then you have basically a bunch of super smart field navigation electronics in there. Then you have, next to your harvester, you have the decommissioning truck coming to take in whatever needs to be taken in. And that has to be exactly precisely controlled, driving next to your farm harvester. So that in the end, if you look at that, this is exactly, again, tactile speed, 1 millisecond control for controlling exactly these kind of things. Today, it's done with humans because machines can't do that yet. We need this 1 millisecond control to run these control loops. But in tomorrow, we will want to be able to just have the harvester itself being manned, and all the other trucks and engines around it will be unmanned. So that all this here happens completely automatically. So there's a revolution ahead. Yes, and if we think of this as now big harvesters only, we want to take this obviously to all kinds of fields and produce way more agricultural goods. The efficiency of the fields could most likely be increased by 3 dB in many countries on the planet if we were able to build these kind of robotic systems, also for small rice fields and whatever, all over the place. So there's a revolution ahead. Let's have a look at it. What is it? It is a revolution as we have had it 20 years ago. We had cordless phones, and everybody thought cordless phones are the answer to everything. Then we found out cordless phones have a limited reach. It's not really the thing. So the ubiquitous access made cellular so cool. If we now take this to the next level, we say it's ubiquitous access also with the Internet of Things. Fine. Or Internet of Everything. What I was talking about is a different stage. We have a limited access remote controls. Today, if you go to whatever, controlling a crane and a building site, construction site, controlling whatever, and the next thing will be have an infrastructure to drive and run controls and have an impact in all kinds of fields. If we look at the impact for the world's GDP of this kind of thing, it can be easily a double-digit increase in the world's GDP, bigger than what cellular did. So what does research have to focus on? We have to be able to build a wireless infrastructure in the networks. We have to be able to show that we can build these things in silicon systems with all the embedded computing involved as well. We have to make sure that we have a mobile edge cloud. The cloud controlling these services cannot be sitting in Alaska. That's many milliseconds away. It has to be way closer to us. It has to be in the edge, in the base stations, all over the place. And obviously, we have to look at applications. We have to look at verticals, industries, and see what's happening there. So we joined up, built the 5G Lab Germany, which is again, like here in Austin, Texas, 20 professors getting together, having fun. And we have 8 companies supporting us so far. You see Claas, our harvesting company, being one of them. We're exactly developing what I was talking about for the harvesters in the first case, taking this to then way more complex systems in the second and third phase. That's just one example. Obviously, 5G is, as I mentioned, these 3 axes. Yes, massive reduction in latency, massive increase in data rate, and massive sensing. But it also is about high security, yes, because we want to make sure end-to-end security. If every KUKA robot or ABB robot or whatever robot on the world is connected to the internet, We have to make sure that you cannot mess up with it and it doesn't start smashing the cars. And it should produce cars. So we need massive safety security. We need massive resilience. We have to be able to build wireless systems that have a reliability as good as a fiber optic cable. And the good news is it's possible. All we need to do is use a little bit of diversity and we're there. Now let's have a look at the millisecond impact as such and look at a little more technology. We see we want to go from a sensor through the embedded computer. We have embedded systems typically in the sensor. Through the transmitter, receiver, the computer, the hosted computing decider, and then back to an actuator in a millisecond. For many applications, we need a millisecond. Some we have more relaxed, sometimes 2 or 3 or 4, so it doesn't necessarily have to be exactly 1 millisecond with all these applications, don't get me wrong. But if we want to hit the millisecond, we probably have around 100 microseconds for the complete transceiving. Yes, collecting the bits, building a packet, transmitting them, receiving them, demodulate them in 100 microseconds. Just transmitting one single bit in LTE takes 70 microseconds. Yeah, that's the duration of an OFDM symbol in LTE. So obviously, we do need a new physical air interface. So it is yet another story about a new air interface. And so the question is, what is it? We need this new air interface, but it should be scalable in bandwidth, right? Because, I mean, some cases we have a megahertz, some cases we have 2, 3, 17, whatever we have available we want to use. We also, if you ever have designed a handset, base stations is not the biggest problem, a handset, terminal chip. In my industry time, I did this. And if you build these systems, one of the biggest problems is designing the clocking system in your handset with all these different clocking schemes. So you don't want to mess up with that. You want to hopefully keep the LTE clocking scheme lively, available, and running. The third thing, obviously, is the spectrum is available. At 100 gigs and beyond, we have plenty of spectrum, but we also have to build centimeter range devices for longer range coverage. And now if we do that, we have to address fragmented spectrum. In developed countries like US, North America, Europe, it's not such an issue. But in developing countries, it's a major issue, bigger issue even than in developed countries. Why? Because they buy military equipment from Russia and from the US, and they hog different spectrum. So the little bit that is left is scattered all over the place. And that's why basically fragmented spectrum is a big, big challenge in plenty of the countries on the planet. Then obviously for getting these sensors to work, I didn't talk much about that, we also want asynchronous operations, so synchronism has to be not a requirement, otherwise we don't get the AAA battery lifetime of 10 years. And when we need a packet latency, not a bit latency, a packet latency of 100 microseconds. So what can we do? Obviously, MultiCarrier is great. Because then we can basically, like here, have 6 subcarriers sitting there in frequency next to each other, and we then can put in 12, 17, how many we need, depending upon the bandwidth that we have. So MultiCarrier is great. But if this was an OFDM symbol, we certainly have to reduce it in time. That doesn't come for free. The subcarrier spacing has to be increased. Now, if we increase the subcarrier spacing, what do we get? As a physical layer guy, I can tell you we get frequency selectivity per subcarrier. So the whole idea of OFDM, orthogonal frequency division multiplexing, is that these subcarriers see a flat channel, and then we receive them, an OFDM symbol, and the subcarriers again are orthogonal. However, if we now have to reduce this in time, we're going to receive a non-orthogonal signal. This is exactly the same as we had in CDMA. Yes, in CDMA, you could build gold codes to make a purely orthogonal system. On the transmit side, but your inner symbol interference will kill this, and so we use PN codes instead because they're just as good as gold codes after sending them through a channel. So here, we're starting out with an orthogonal modulation system and receiving a non-orthogonal system. So the question is, do we really have to start out orthogonally? We don't need to necessarily have to start out orthogonally. So let's have another look at MultiCarrier. What are some of the advantages? The cool advantage of MultiCarrier is actually that we have, in this case, like 4 subcarriers. Everything is nice. What we do is we copy the latter part to the front, put in a cyclic prefix. This depends exactly on the speed of light and the circumstances you're looking at. So basically, the cyclic prefix captures your inner symbol interference and your group delay of the filters, hopefully as well, of your analog front end. And with this, basically, we can build a circular system, do the signal processing with FFTs, and make it as easy as possible. That's the reason why, if you look at it, the signal processing per bit of an LTE modem is less than 10% compared to CDMA modem. Yes, so the number crunching we need per bit is so low, and that's why we can build these very low-cost LTE systems. So that, and Wi-Fi systems as well. So OFDM has a fantastic advantage, low signal processing complexity based on this. Now we have a problem. We have to put in multiple of these, and they're short and whatever. What can we do? Well, the good news is nobody told us just to put in one symbol. We can actually put in, like in this case, 8 symbols in a row. If we take 8 symbols in a row, suddenly we can do something we couldn't do before. Now, per subcarrier, we have 8 symbols, meaning multiple symbols. Now we can do filtering per subcarrier. So we can do some kind of a filtering, cyclic filtering, tail biting filtering. Then it becomes a pure FFT operation. And then capture the last part and put it in there as a cyclic prefix, and off we go. And then we have overlapping subcarriers, possibly non-orthogonal. So is that an issue? I'll have a look at that. So with OFDM, it's clear we have n subcarriers, in this case a resource block of 12 subcarriers. We have the cyclic prefix, everything's fine. In single carrier FDM, like in the LTE uplink, we have 12 symbols in time. We capture the latter part, put it up front, and we again have the cyclic prefix, and we have the FFT-based frequency domain equalization techniques that we all like and know. And nobody tells us that we have to stack all bits in frequency, all bits in time. We can do some intermediate part, and that is basically the generalization of it. So that's a generalized form, generalized frequency division multiplexing, where we just say, now we can stack the bits and pieces as needed. The good news now is that with this, we can do cyclic filtering, tail biting filtering, Jack Wolf's idea for convolutional codes applied to signal processing. And then basically take the latter part, put it in as a cyclic prefix, and off we go. What can we get? We can get super deep notches, as you can see here, all the way to below 60 dB notches between systems, which is exactly addressing our issue. Because if we want to address scattered spectrum and you want to build a handset with a low-cost solution, you have to put in all kinds of analog filters, depending upon, and you have to switch your analog filters when you go from here to India to China to Japan or wherever you're going. So that's not the solution. So we have to have a way of suppressing the signal by more than 60 dB between scattered spectrum as here. Then the question obviously always comes up is, FBMC can do this? Yes, FBMC can do this. And if you look at it and look to the matrix formulation, FBMC can be formulated as a special case of GFDM. But still, FBMC has one major issue. Everybody says it doesn't work with MIMO. What is the main challenge? The main challenge in MIMO systems is I have like a 2 transmit antenna, 2 receive antenna system. And because in OFDM the subcarriers are staying orthogonal from a transmit to the receive side, we can actually do per subcarrier MIMO demodulation, and things become much easier. If we now have leakage from one subcarrier to the neighboring subcarriers, it becomes a little more of an issue. We have intercarrier interference, and we have to deal with that. And you can see here, it can be dealt with very nicely, and obviously the best way to deal with that is just using what we do as communications guys today anyway, build a turbo receiver where the decoder and the soft input are basically coupled backwards in a loop, and you subtract the interference. While you do that, have a parallel interference cancellation basically based on that from subcarriers to subcarriers. And if you look at that, with 2 iterations, you have the blue curves, and you see OFDM clearly outperforms GFDM, but with 4 iterations, surprise, surprise, what happened? How can that be? Yes, I mean, this is a 4x4, 16 QAM typical channel with a delay spread, and still, how can GFDM be better? Yes, when I looked at these curves, I didn't believe my students. And it's a very simple thing that you have to realize. If we build points in space, like your 16 QAM, points in space, we're putting it on a 2-dimensional grid, orthogonally, in phase and quadrature phase. And we're spacing them nicely. Obviously, if we were to space them like this on a hexagonal grid, we would gain 0.5 dB. And what is happening here is due to these, if you choose the filter right, your cyclic filter right, you actually, with the same energy, start spacing the points farther apart. With a 4x4 MIMO, it's an 8-dimensional problem, and you can actually pack the sphere very nicely such that you get this improvement in performance. Here you see basically that it is not only pure theory, but we have a setup here with 2x2 MIMO with the NI equipment. You see the 2 antennas in the middle and 1 antenna on each side. So that's the 2x2 MIMO setup. Here you see on the right-hand side, you see nothing. Now it's turn on the receiver and start synchronizing. And after a couple seconds, since this is not real time, we can actually see here very nicely the single constellation. We get the 16 QAM. This effect of compacting the signals in space happens due to the filtering. On the detection side, we're basically back to normal, what we all have learned in the textbooks. Now from an LTE compatibility point of view, obviously I mentioned that we have to do something here as well. We have to fit into a frame structure. LTE symbol is like this. We have a PRB, a physical resource block with 12 subcarriers. These are 4 PRBs, and this is one single OFDM symbol, and it's only 70 microseconds long. So we could, for example, build a TTI like this, a packet like this, where we have 7 sub-symbols and 8 sub-symbol as the cyclic prefix, and off we go. We're happy, things work out. And then we basically have a 70 microseconds TTI versus a 1 millisecond TTI as it is today in an LTE system. So what do we see? What are the requirements to get back to making the tactile internet happen? Scalable in bandwidth, that's not the latency requirement, that's just a requirement of 5G. For that we want to be multi-carrier. Fragment and spectrum and deep notches, we want to have filtered subcarriers. And for latency and clock reasons, we want to be able to build a packet as small as possible. And that's basically how we do it. And basically, all 3 can be addressed by generalizing the approach of OFDM. And there are plenty of proposals on the planet. And if you put the coefficients of the number of subcarriers, filtering whatever correctly, we typically can just generate them by setting the matrices as such. So with this, the good news is, yes, we can really have short packets. We can improve the spectral efficiency because of this out-of-band filtering of the scattered spectrum. It is very easy to build estimation for channel estimation, synchronization, everything, because it's basically OFDM. It's nothing different, right? You have on modulation size, you have the complete freedom. And it is very small complexity because you do everything with FFTs. And as I've shown, it's MIMO ready, which always has been the big issue with FBMC. So in conclusions, what do we see? I try to give you sort of an intro on what is going to happen in the future. We see that we went from voice to data to video, everything today. And maybe 3D graphics is happening right now if you look at the new products coming out. So I see that by the end of LTE will be a lot in a 3D graphics and whatever kind of space. But the big clue about 5G is not only broader pipe, it is that we get down to our latency down so that we can really extend our touch and feel, have robotics connected to an infrastructure, the tactile internet, as we call it. Then obviously also massive machine-to-machine communication, and then we have to address other things, but Farouk is going to talk about the terabit stuff, so I canceled my slides on that to make sure that I can concentrate on just the one thing. Okay, with this, I would like to thank you all for listening and move on.
We have time for a couple questions. I'm sure it's stimulated many imaginations. Ahmed.
So, Gerhard, I really enjoyed your talk. But for the first part, many of the applications that you provided as motivation can be sold in a different way. So, for example, when I'm looking at the ball coming to me, instead of showing me the ball in real time, you should predict where it's going to be in X number of milliseconds. And that way I would actually catch it. And that's exactly what we do. I mean, if you're a hunter, you don't shoot at the bird, you shoot in front of the bird, right?
Yes, so the question was, if I show the ball, can't I just predict where it's coming, project that in here, and off I go? And that is what I do as a hunter. I shoot in front of the bird, hoping that the bird flies into the bullet. And so the answer here is, this is exactly what control theory does, or control systems do today. Yes, you try to build a control system based on something where you can predict the environment, but you are never able to do the unpredictable thing. So if I'm sitting using my humanoid robot, and suddenly something falls and I want to catch this, I will not be able to catch it because I would have to do all kinds of prediction of all kinds of scenarios. That is impossible. So you're right. There are certain cases where you can predict, and this is what is done also in robotics in many cases. But other cases where you have gravel on the road and whatever all, you cannot predict in the car, and that's why everything in the ESC is in the millisecond range. If you go to factory automation, even in factories where you seemingly can predict everything and the robots are working there, everything, all factory standards are end-to-end 1 millisecond latency. So it turns out that the vast majority of applications, the ones that we want to have the next Facebooks, Googles, and whatever come up with, will be in this unpredictable space. And the few predictable ones are obviously, yes, you could do that way. But I mean, we've talked to architects, yes, and civil engineers. And they're all excited about this because it revolutionizes their way of doing this, yes, of constructing buildings. The architects say, well, we don't have to watch out for scaffolding anymore because we can have these humanoid robots crawling the walls and drones flying around and everything controlled by people. And we can make sure that we have an infrastructure at the construction site so that people don't crash into each other. Other cases where we're talking about putting this into the next level Da Vinci. Yes, so we're talking to the Da Vinci guys. Da Vinci, by the way, is a robot for operations, for surgery. Yes, so if you go and have surgery and you have a robotic system, then it's called a Da Vinci typically. They have 80% market share or whatever. Probably Austin-based company. And there the big problem is exactly the latency, because if you talk to these people trying to do the surgery, it is like, oh, I cut this vessel and I only noticed like a couple milliseconds too late, which is not so cool for the patient. So again, just for having this natural look and feel in many situations, we really need this millisecond. But you're absolutely right. If we fly a remote control heli today, we do exactly what you were talking about. After a while, we get used to it, that it is like a Buick, yes, and so we do exactly what? It's flying towards the wall, and like a couple milliseconds before that already, we start moving the joystick to make sure that it doesn't crash into the wall. Sometimes we don't do it on time, then it does crash in the wall. But I mean, this is exactly this predictive kind of thing that we also learn doing as humans. So that's why you're absolutely right. It's not strict that every single application needs exactly 1 millisecond. Yes. Long answer.
Yeah, so I think we're actually out of time. I'm sure there's many, many more questions, but Gerhard will be here at the break, which we'll have in about 20 minutes, and so I'm sure we'll take all your questions then. Okay. Thank Gerhard for the very great talk. All right, so our next speaker is Farouk Khan. So Farouk is the president of Samsung Research